Hello, this is Mr. Bus, and in this video, I will go through the three-dimensional molecular model building activity that we did today in AP Biology. All right, and so in this activity, we used, excuse me, this model building kit where each of these is going to represent a specific atom or element. So this one, for instance, has four places where a bond is going to go. And so this is actually carbon, because if you remember, carbon needs four bonds because it needs to share four electrons, because it has four electrons and it wants four more. So this is going to be carbon. This red one only has two places that there can be bonds, and so this is oxygen. This can represent other things too, but this will be oxygen. Because oxygen has 6 valence electrons, and so it needs 2 more to be shared with it, so 2 bonds. This blue one will be nitrogen, and so on. And these little ones are going to be hydrogen. So, and then the connectors, okay, these are going to represent the pairs of shared electrons, right? So the pairs of shared electrons, so I'll just turn to page 20, our book here. So, kind of remember what we did before, where we took, like, this is an example of like methane, where you had carbon atoms, and you took like 4 hydrogen, and then those hydrogen shared electrons, and the carbon shared its electrons, and then you have this completed valence, right? So carbon has now 8 in its outer energy level, and each hydrogen has 2, so it's happy. And then so we kind of did this dot diagram structure with the chips the other day. And again, what we're going to use today is we're just going to use these lines. So each line, like between a carbon and a hydrogen, that line is really representing a pair of shared electrons, okay? And the nice thing about the model building kit is that it helps us to see the three-dimensional structures as well. And we're also going to be, a purpose of this, one of the things we're going to really do with this is we're going to be referencing page 23 in the book, and we're going to see, as we build these models, if they have functional groups on them. So these are basically, functional groups are common atom combinations of atoms that you'll see, like OH is a common combination that you'll see, and that's a hydroxyl group. C double bonded to an O with an H on it is a common one called an aldehyde. And this R is just representing that this OH is attached to, like, I call it like a carbon something. So it's attached to something, right? So if you see an OH attached to something, it's a hydroxyl. If you see a C double bonded to O with an H attached to something, that's an aldehyde. So, and again, there's keto, carboxyl, amino, phosphate, and sulfhydryl on here. So that's, again, a purpose of this, is to use this activity to build some structures and then to see what kind of functional groups there are, as well as, reminding ourselves if we understand polarity, right? So if the molecules are polar or not would be good to look at as well. So here is a little guide we used in class. And so, like, the first one I'm going to build, I'm going to move this a little closer and I'll zoom in here. We'll just build carbon dioxide, CO2, okay? So carbon dioxide has carbon in the middle and oxygens on the outside. 1 carbon, 2 oxygens. Notice there's 2 lines between the carbon and the oxygen here and here. That means that carbon is going to have double bonds to the oxygen. So this is a carbon atom, and I'm going to use these flexible connectors as opposed to these little ones are more rigid. I'm going to use the flexible ones here because these flexible ones are much better at forming double bonds. So there's carbon double bonded to 1 oxygen. Okay. And then I'm going to go carbon double bonded to another oxygen. So again, this is kind of how this is going to work. Here's CO2. Carbon is happy because it has 1, 2, 3, 4 pairs of shared electrons, meaning there are 2, 4, 6, 8 electrons in its valence. And oxygen is happy because it has electrons out here that are lone pairs that are not shown. That is, I guess, one deficit here, is you don't see the lone pairs. Oxygen has 2 lone pairs, and then it has 2 bonded pairs, so it has 2, 4, 6, 8. You don't see those, but oxygen does have the 2 bonds that it needs to fulfill its valence. So there's CO2. And then I guess I asked in class, is this non-polar covalent, polar covalent, or ionic? So you just kind of look at, remember how we did that? Okay, in the book, we looked at the electronegativities table. Oops, I don't know if you can see that or not. And then, you know, okay, we have oxygen, which is 3.4, double bonded to carbons, which are 2.6, 3.4 and 2.6, the difference is 0.8. 0.8 is significant enough. It's between 0.5 and 2 was the rule that we used to call that a polar bond. So these are polar bonds where oxygen is going to be partially negative, carbon is partially positive, partial negative, partial positive, and so this would be considered a polar molecule. Okay, let's build another one, a little more complex one. All right, so we're going to build ethanoic acid next. So with this one, we've got a CH3, and then we've got another carbon, and that carbon has a C double bonded to an O and an OH. So CH3, COOH. CH3, COOH is how I would read that. So let's build that. Let's build ethanoic acid or vinegar. I'll take apart my carbon dioxide here. Excellent. All right. CH3. I'll build that first. So CH3, there's a C, and then I'm going to have to put 3 H's on that. 1, 2, and 3. Oops, H. So there's a CH3, and that CH3 is going to be attached to another carbon with a single bond. Okay, there's a CH3, and this is going to be the COOH. So that's going to have the double bonded O and the OH on it. So I will need to do a double bonded O. So I will do like looking like that. So there's the CH3C double bonded to an O, and then I'm going to put the OH on the end there. All right, and then that OH is going to look like this. All right, so that is ethanoic acid. Oh, I'm sorry, not ethanoic acid. Yeah, ethanoic acid or vinegar. All right, and then what we did in class is we took a look at that and said, okay, how does that relate to polarity and how does that relate to our functional groups? So ethanoic acid has a R group. That would be CH3. That's just the carbon something group. Okay, and then this would be the functional group. This would be the carbon double bonded to an oxygen and an OH. This is going to be one of these functional groups. And so if you look at it, it happens to be, even though there's an OH on it, it's more complex than that. It's not just an OH. It's actually got the OH, but it's also got this going on. So because it has all that stuff happening there, C double bonded to with an OH, you're going to call that a carboxyl group. Okay, this is the R group right here, the CH3, that's the R group. And then this right here is the functional group, the C double bonded to an O and OH. So basically what we did in class is we built these structures and try to find the functional groups as we did that. And so this happens to be a polar molecule as well. How do I know that? I know that because carbon is a, what is the electronegativity of carbon? Carbon is a 2.6, and oxygen is a 3.4. Difference between 2.6 and 3.4 is 0.8. So this is polar. This is polar. Difference between oxygen and hydrogen. Oxygen is 3.4, hydrogen is 2.2. Difference is 1.2, also polar. So there's tons of polar interactions on here, and I'm just going to make a water molecule super quick to show why that's important. So if I put together a water molecule really quick, H2O, remember that a water molecule has polarity. Whoops, I forgot an H. So this is partial negative, this is partial positive. This is partial positive. So what's going to happen with vinegar, which happens to like water, right? Vinegar, if you buy some vinegar and add some water to it, it's just watered down vinegar and it mixes. Whereas like if you buy oil and you try to mix it with vinegar, it's not going to, or oil, and mix it with water, it's not going to mix. And why is that? It's because water molecules will interact, right? So the partial negative of the oxygen here will interact with the partial positive there, and a water molecule might position itself like this, where these are close to each other. Or the hydrogen and the oxygen might interact like this, where they get close to each other and form a hydrogen bond, okay? Or here, okay? So you always have these opposites attracting, partial negatives attracted to partial positives. So if this is a polar molecule, what it means is other polar molecules, like water, they play nice together, okay? Water's not going to really interact with the CH3 part because these are not polar bonds right here. These are non-polar. But the molecule is considered polar because there are a few polar interactions. If you have a small molecule with at least one polar region, it's a polar molecule. It will mix with water, it will play nice with water. If you had a huge structure, like in the book here, it shows us like this large complex molecule with some polar regions. Those polar regions will interact with water, but the other regions won't. But small molecule has some polarity to it, so it's a polar molecule, interacts well with another polar molecule, like that, or like that, or like that. So I hope that makes sense. I'm not going to build all of them in the video here because the video would probably take half an hour. I just wanted to show you kind of what we did in class. We built ethanoic acid. We built vinyl chloride, which does not really have any functional groups on it. We just built it to show what that would look like. We built ethanol. Look at that. There's an OH. There's a functional group. That's a hydroxyl group. We built ethanal, which has a different functional group there, C double bonded to an O with an H on it. Should be an aldehyde. We built acetone, which has C double bonded to an O in the middle of two C's there. So that would be a ketone or a keto group. We built an amino acid. We built glycine. Glycine has a carboxyl group and an amino group. So if you'd like to work with these in the room, I have the structures. I just wanted to show you kind of how that works, and I wanted to give you the intro that I gave the class about how to build these. What we did is we then took pictures, and then we'd circle, like that's carboxyl group. That's the R group. And then I would say, okay, you could label that as partial negative, that is partial positive. You could label that as partial positive, that is partial negative. So we kind of like talked about polarity. Again, refreshed our memory about polarity. We refreshed our memory about bonding and valence electrons, and then built these three-dimensional structures to kind of see how this all would look in three-dimensional space. So hope that was helpful. Take it easy.